What's up, everybody? Alan here, coming with the last section of this chapter on algebraically defined vectors and this thing we're going to call the dot product. So without further ado, here we go. So we've talked about geometrically defining these vectors and what they look like and some of their attributes. Now we're going to look at that directed line we call the vector to see if we can represent it algebraically with equations and variables. And so I've already drawn out a vector here. And again, that's going to get us to a certain point. So this point right here. And if I was to algebraically say what that is, normally we would have started at our origin of our XY axis, and we would have marched over from the origin some distance, x, and then from there we would have gone up some distance, y. And we would have called that point xy. Now, normally that's what we would have done on all of our Cartesian coordinate plane, our rectangular coordinates. And we would have formed that right angle there, and we would have called that a point, a coordinate, ordered pair. So the only difference is with these, instead of being on the rectangular, we are obviously still within this realm, but instead of calling them x and y like we have in the past, we're now going to call them a and b and get to this point AB. And instead of having that length that we had originally from the origin stretched all the way out being called R, and then rotating that around on our unit circle, then this length of R is now what we're calling our vector, which they'll either give you as a bolded letter or a what it looks like ray or directed line over the top of it to let you know it's a vector. And so remember, our length, we call the magnitude for these vectors, is going to be represented by this absolute value, which remember we did that because our radius, length of our circle, was always a positive value, a distance. And so all we're basically doing with this is changing out these variables, x and y. We're still going to be utilizing this whole theta and u or r, right? But instead of x and y, we're going to be using a's and b's. So in order to find some of these things, we're going to actually have to solve. And remember, we said that if we used cosine of the angle and we knew the x, y, and r values, then we knew cosine was always the x over the r. And similarly, we said sine of that angle theta, we called it, would be our y over our r. And so we could actually solve for our x and our y, but remember the only thing that we're going to do is replace the x with an a, the y with b, and our r with u. That's the big change from what we've always done in the past since the beginning of this class until now. And so all we're left with having to do is multiply over by that u or that r that we had originally. And we will say that now we have our a is equal to u times the cosine of theta. Now we can represent that distance there, that point at the end of our vector, to be u cosine theta, which again, if I just rewrote it in our old terms, we would have had this as x equals r cos theta, just to show you the comparison. And if we did the same thing over here, we multiplied over by that u to both sides, because who doesn't like u, you know what I mean? So that would then give us our b variable is equal to u times the sine of our angle theta. Which again, if we wrote it in our old terms, that b value was what we said would be our y length, and the u would be our r sine theta. We've already gone over this stuff, the basics of Vector land is we're changing the variables so that you know we're dealing with vectors and not our rectangular coordinate plane. So not too bad, not much of a change here, but remember, this is for when we know our x, y, and r, which we are then changing to a, b, and our vector u or v, whatever they want to call it, okay? But what if we had theta and u, and we did not have our a and our b? So we want to be able to work both directions, okay? So if we wanted to find a and b, then we need to know u and theta. But what if it was the other way around? Okay, what if we now know a and b, which to let you know it's not just an x comma y as a rectangular coordinate point, they're going to put a different type of parenthesis that you can see there kind of resembles a v to let you know, hey, this is a vector. We're getting there. So if I know a and b, then how would I find our vector length, which we're going to call the magnitude, and the angle? Well, remember, that was just our r that we talked about, and theta is always theta. So if we have this right triangle over here again that we started with originally, right here, then if I know the a and the b, obviously, if I have this right triangle, then I can use what to find that length we used to call r, which is now our magnitude of our vector, the length of our vector. In a right triangle, if we know 2 out of the 3 sides, that's right, we can use the Pythagorean theorem. So all we have to do to find u, the length of it, we call the magnitude, is just set up our Pythagorean theorem, which remember would be a squared plus b squared equals that u squared. So then we would have to take the square root of this whole thing to find the length or magnitude of our vector. Again, guys, nothing has really changed. This is still the same thing that we've been dealing with, except different letters. Remember, it used to be x squared plus y squared equals r squared. And to find the r, we took the square root, and we had r is equal to the square root of our 2 legs, right? So again, very similar to what we have been doing in the past for quite some time, but new letters. So lastly, to find theta, remember if we had our x and y, which we're now calling a and b, then that from theta would be the opposite over the adjacent, which means y over x, we would be using tangent of that angle. But in order to find theta, remember we have to take and use the inverse in order to reverse our input and output. So in order to find this one, we would just take the inverse tangent of our, now remember, instead of y and x, we're going to use b over a. And that will give us our angle theta, just like we've done in the past. So don't be too scared of this physics application that we're learning, the mathematics behind with vectors, because it's virtually the same. But to let you know we're in vector land rather than our Cartesian or rectangular coordinate plane, we're going to change the letters and the way that we write our parentheses for points. All right. So here is all of that so that you have it for your notes in a little bit clearer version. But I just wanted to quickly derive that for you. But like I said, the main thing I wanted you to be able to see is it's virtually the same as our rectangular forms that we've already been working with. The only thing that's going to be new or different is the format. And that's by changing our x and y to a and b, and our r to a u or a v, whatever they want to call our vector, and the arrowheads and brackets will have those V-looking shapes rather than our parentheses. All right, so let's take a look at a couple of examples, and then we'll add in a few other parts and keep rolling. So let's find the magnitude or length, and also they're going to call it the direction angle or theta for this, which again you can see is bolded, or they'll put an arrow over the top. It's easier to just bold it when typing out, so that's how most books will have it. Okay, when we're writing it out, we don't want to sit there and have to bold it with our pen or pencil, so we usually just put the arrow over the top to represent the vector. Okay, but again, hopefully you recognize that this is virtually just this. So we already know that we should be in quadrant what? Hopefully you said quadrant 2. So when I go to draw this, I know I'm going to be dealing in quadrant 2, and I'm going to be going just like I always had, -5 to the left, and then +4 up. And that's going to get me to this point, which again, we're just going to write a little bit differently as a vector, which means in order to connect that, I will then take and draw and put an arrow at the end. That's the only difference, right? So now I can have my angle theta. To the left, I know was -5 and up 4 to get to that point, and I now have my right triangle. So when they ask me to find the magnitude, I know that I can find this vector, which they're calling u, and I need to find that length. And we know we're going to do that by a simple Pythagorean theorem, which would be -5 squared plus 4 squared equals our vector u squared. And now we have the length, just like we've always done, just using different letters. And in order to find that, they're calling the direction angle, or theta. We will do something similar, but this time we only have these two values, which is my typical y and x. They're now calling it b and a. And in order to find theta, I'm going to have to use the inverse, because I'm trying to find an angle, for tangent, which I know is usually the y over the x. And plugging that into your calculator, you will get out an answer of 141.3 degrees. So just make sure that you round it to the nearest decimal place, or whatever they ask you to, in this case, the 10th. Pretty simple, not a whole lot new, just the formatting of it and the look. So this should excite you a little bit, and notice that this is everything that we've already studied in this class up to this point, except the look of it. So that's exciting, because we should already feel very comfortable with this, and just working it out changes the look of it with new variables. So remember I said that we need to be able to work both directions on this. So this time they're calling it a vector v, and this time they're telling us the length or the magnitude, and they're giving us the direction angle. So remember, when I first started example 1, I asked you all what quadrant we would be located in. Well, this time, hopefully you can also see what quadrant we would be located in, because they told us we have a 220-degree angle. And because we have that, you should immediately think, all right, that's 180 degrees plus a little bit more, not quite another 90 to get to 270. So we should be in quadrant 3 somewhere. So I'm going to go ahead and draw that over here again, just to have my visual. And so I know I'm going to rotate 180 degrees plus how much more? And hopefully you said 40. Now, why is that important? Because then I know my reference angle. So now I have my vector, which I can say that theta is 40 degrees as a reference, right? To go that 180 plus 40 more to get my total of 220. And then they also told us that this length, which they called it v, that magnitude is 14.5 in length, whether that's inches, centimeters, what have you. They didn't label it. So to us, we won't talk about it. So what we then need to do is drop our perpendicular so we can create our, of course, right triangle. We've dealt with all kinds of triangles now, oblique as well, but we prefer right. And we need to be able to find this direction that is going to the left, which remember usually was our x value, and then our y value, which is going down. So already, remember we said instead of x and y, we're going to call it a and b. No big deal there. But already I know that this point, this vector that we're going to find, is now going to be negative something and negative something. That's the only way to get to this point right here, which is at the end or tip of our vector. All right, so again, nothing new here, but in order to find our x value, remember it was x equals r cos theta. And to get our y value, it was r sine theta. Well, to put this in, instead of a ordered pair, to make it our vector, we will change our parentheses to be more of a V shape. And instead of x, it will be called a. And instead of r, we called it v or u in its length times cos theta. And instead of y, we called it b and the magnitude of our vector v. So that's it. All you got to do is plug that stuff in and you will get your negative values. So just make sure that you get the correct placement of our vector, which is going to be dependent on both its magnitude of 14.5 and obviously its directional angle theta 220. So what should we actually use for theta? The 40-degree reference angle or the 220-degree? Remember, the reference angle is only going to give us the value. We actually want the 220-degree placement in quadrant 3. So when we go and fill all of this in, we're actually going to use our vector length, which they already gave us, times the cosine of the actual angle that they gave us, 220. And then same thing here, 14.5 times, now for our y value, which we're calling b, would be the sine of that 220 degrees. And after punching that into our calculator, we should get an answer of, to the nearest tenth, negative 11.1, comma, negative 9.3. So hopefully you were able to find that in your calculator and work that out. Pretty simple stuff, but again, make sure that your calculator is correct and your setup. So the second half of this section is going to be about some of the operations, the things that we can do with vectors. And they play a very similar role to what we've always been able to do with adding, subtracting, multiplying, and dividing. And that is only like things. So when we're given an x and a y in a vector, and then another x and a y in a vector, if they ask us to add, then we're only going to be able to add the like things. So the x values and then the y values. And that will give us a new length of a vector. Oftentimes, what is called a resultant vector. The result when we added two vectors together, two forces. Okay. Also, if we multiplied some constant times a vector, then we basically just do what we normally would have done if that was a set of parentheses here. We distribute to each of the x and the y values, or what we're calling a and b. All right. So whether it's some random number or constant, or we write it as u and we multiply by the negative. Remember, we called that the equilibriant oftentimes. Then the only thing that would change is the fact that we'd be multiplying by a negative. It'd be facing the, remember the term we used for negative is the opposite direction. right? The values of A and B would not change because it's multiplied by -1, right? And whether we're asked to add or subtract, same thing, we can only do like terms. So the A minus the C is what we would have here, and then the B minus the D. That would be my other resultant vector. Now, sometimes these get a little bit laborsome to write, and some people's vector start looking like parentheses. So another form that we can write these in is, rather than those vector braces that we'd have on, instead of our parentheses, they will use what are called I's and J's. An I is basically just the A or X part of it, which is meaning we don't have the Y value for that part. And then the J would be our Y value, meaning we don't have the X or A value. It's only the B. All right, so that's just another form, another way for us to try to confuse students, of course, right? No, that's not the reasoning. It's just so that we have a better way of writing these things. We can just write it like this, with I's and J's representing in alphabetical order, rather than these weird vector braces instead. Okay, so the last part that we're going to be dealing with is something called the dot product. And so this is one that we're going to have to make sure that we emphasize, and then we'll do a few examples of all this stuff and call it good. So the dot product, make sure that you write notes and have this somewhere, is when we have two vectors, call them u and v, right? And again, this, be very, very careful, is different than when we're multiplying, even though it looks very similar to our multiplication symbol. So I always like to overemphasize if it's the dot product, and I will write that dot very, very largely so that I know it's the dot product and not multiplication. All right. And we'll say it as u dot v to make sure that we don't mix it up as multiplication. And so, just like I mentioned before, whenever we are adding, subtracting, or multiplying by some constant, we could only add, subtract, multiply to like things. So when we are doing the dot product of these two vectors, we are only going to multiply the like terms. So the A and the C first, and then we're going to multiply the other two like terms, our B or Y values. And then what happens when we ask us to do the dot product is, when we multiply those two values, we will then take and add to get some number. So that's different than all the stuff that we went over up here, because as you notice, all of these left us with vectors. But the dot product actually yields a number, which, if you remember, we called a scalar. Okay, so it does not yield another vector, but a real number called a scalar. So that is the difference between the dot product and multiplication. Okay, we will also use it to find a bunch of different variations of it, which is pretty cool. Doesn't matter what order we multiply or gather these things in. Remember, this was called the commutative associative property, right? When we multiply a vector times 0, we still get 0. All these things that we learned in algebra still holds, but we can also use that dot product to find angles between two vectors. Okay, so remember, up here, this is actually going to be the dot product, right? And the dot product, remember, I like to overemphasize and put a big dot so I know it's not multiplication, right? So in order to find an angle between two vectors, they're calling u and v, we're going to have to take the dot product on top over their magnitude multiplication on bottom, right? So be careful with that to help you remember it. That hopefully will help you remember. In order to find it, it's going to be, remember, the last law that we learned was the law of cosines, and that was usually when we had to find an angle before we could use the law of sines. So it's going to be the dot product over the multiple of their magnitudes. right? So make sure you write that in your notes. And in order to figure out what the dot product is going to give us, if it comes out positive, it will yield an acute angle. Okay? If it comes out negative, it will yield an obtuse angle. Because remember, all students. So if it's positive, that means it's acute. It's between 0 and 90. Right? If it's negative, it will be in this quadrant, because remember, we're going to have to take the inverse in order to find the angle itself. And so that's why it's going to be between 0 and 180, because when we were finding inverses, remember, we couldn't use quadrant 4, which would have just been negative acute angles, because it was also positive like it was in quadrant 1. So we had to go to quadrant 2. And if it comes out 0, then that means it's right in between those, which would mean it would be a right angle right there. All right, so that is all the definitions in here. Don't worry too much about these, because whatever you think that you would have done based on all of your previous experience, all that basically is saying is that they hold true, just like we always have done. So that's nice about vector land, but the main things are going to be this dot product, and then also the geometric interpretation of it, which is basically just to find the angle theta, all right, which is just the dot product on top over the multiple of the magnitudes. So let's do a few examples with this and then let you go practice. So first thing we're going to look at is, what if we were just asked to add these two vectors, u and v, which they named here and here. I bolded them. Most of you would just write the arrows over the top. So if we were asked to add u and v, that literally just means add the like terms. So I'm going to take the 6 plus the negative 14, and that's going to be the a, or the x values, and then I will take negative 3 and add it to the 8, and that will be my b, or y values. And so my final answer there is still a vector, which would be 6 minus 14, definitely negative. And now just do 14 minus 6, which would be 8. And then negative 3 plus 8, which again would be positive, and 5. That's it. I know that seems a little too simple. And then you're like, and then what do we do? That's it, you guys. So don't make this more difficult than it is. Just do what it says and add what you already know how to add. And that's the a values, or x's, and then your b values, or y's. So careful, I'm going to rewrite the next one. It says to take negative 1/2 times our vector v. So in this case, we're only looking at vector v, which is the negative 14, 8, and they're virtually telling us to multiply both of these things by negative 1/2. So again, just be careful with the negative. Otherwise, negative times negative is positive. 1/2 of 14 is 7. And then negative times a positive is negative. Half of 8 is 4. That's it. So this last version I wanted to show you, again, very simple, but be careful. A little bit more going on with these vectors. They want us to do 3 parts. First, multiply these by individually 5 to the u and 2 to the v, and then lastly add. And again, we're going to add the like terms. So doing 5 times u, go ahead and do that, and then plus 2 times v would be a setup like so. Distributing that into my vector would give me a new vector that is 5 times bigger, of 30 comma negative 15, plus distributing that in, getting twice as big, negative 28 comma 16. And now adding the like terms would give me, adding 30 and negative 28, a new vector of 2, and then negative 15 plus 16 would give me 1. Doesn't get much easier than this, but again, just be very careful. Don't make a silly mistake and get frustrated by losing a negative or trying to do too much. Keep it simple.